Today's lesson is on medians and altitudes. So let's just take a second to review. Last time we learned about circumcenters and incenters, and you should have a really good grasp on what those two things are now, whether they're on, outside, or inside the triangle, what they're equidistant from. So I hope you got all that mastered, because here we go with two new things. We've got a median, which is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. That's a median. And let me show you what that looks like, what I'm talking about here. Median of the triangle. A segment whose endpoints are a vertex of the triangle, so there's one endpoint, and the midpoint of the opposite side. So I would need the opposite side over here, find the midpoint, and then when I draw that segment from this vertex to the midpoint of the opposite side, that's a median. Okay, let me do another one. There are three. Vertex, midpoint of the opposite side. Okay, one more. We'd have vertex, midpoint of the opposite side. And look what happened. Once again, we got a point of concurrency, and that point of concurrency is called the centroid. The centroid is the point of concurrency of the medians of a triangle. And interestingly, you remember how I told you there's so many fascinating things in this unit? This centroid is also called the balancing point. Balancing point of the triangle. So you got a triangle, you find its incenter, and then let's say you take the point of your pencil and you place that triangle's centroid right on the tip of your pencil. That triangle should balance there. It will if the circumstances are right. Centroid is the balancing point. It's the point of concurrency of the medians of the triangle. And we have a theorem that says the medians of a triangle intersect at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, so what is that saying? It's saying the centroid, that's that point that's 2/3 the distance from each vertex to the midpoint of the other side. Okay, so let's look at this triangle here. So AP, here's AP. So that's the distance. So P in this triangle, P is the centroid. So the distance from the vertex to P is 2/3 the length of that entire median. So that median is AD. All right, that's all that theorem is telling us. So BP, the length from the vertex to the centroid is 2/3 the length of the median. So CP is 2/3 the length of CE. Excuse me. It's all that is telling us. For any triangle, the centroid is always inside the triangle. And of course, since I told you the centroid is the balancing point of the triangle, that stands to reason, right? You can't possibly have a balancing point that is outside or on the triangle. Always inside the triangle. Okay? The perpendicular segment from a vertex to the opposite side. So let's look here. Perpendicular segment from a vertex to the opposite side. So I need a perpendicular here. That is called an altitude. And we've known that, right? We've known an altitude is the perpendicular. It's the height, right? It's the height of the triangle. That would be the height of the triangle. Let's see if we came from this vertex. If we came from this vertex and found an altitude, That would be an altitude right there. That would be the height of the triangle. If I came from the other vertex, I'm going to say probably like that. Oh, shocking. They're concurrent. What do you know? Okay, but look at this. It says from a vertex to the opposite side or to the line that contains the opposite side. Okay, so let me show you what that means. We need the line that contains the opposite side if we have an obtuse triangle. So let's look at this one here. Obtuse triangle. Okay, so there's an altitude, right? But what if I want to come from this vertex to the opposite side? There's no way I can get to this opposite side with a perpendicular unless I extend this side. So that's what I got to do. In the case of an obtuse triangle, I got to extend that side so that I can drop a perpendicular. So there's that altitude. And then likewise, if I was trying to come from this vertex to the opposite side, I would not be able to get a perpendicular unless I extend this side. Then I can drop my perpendicular. And what's going to happen is those three lines, those three altitudes are still concurrent, but I'm going to have to extend them to find the point of concurrency. And that's going to be way out there outside of the triangle. So the altitude, the point of concurrency of the altitudes, just like the circumcenter, could be inside, outside, or on, and this point of concurrency is called the orthocenter, the triangle's orthocenter. Okay, so here's a theorem. Concurrency of altitudes theorem. The lines containing the altitudes of a triangle are concurrent if HE, BD, and CF, so here we go, HE, CD, no, BD, sorry, BD, and CF are the altitudes of triangle ABC, then the lines HE, BD, and CF intersect at some point. In this case, we called it A. The lines containing the altitudes of a triangle are concurrent. Okay, so there's our orthocenter. Here's our orthocenter on an obtuse triangle. Here's our orthocenter for an acute triangle. I wonder what interesting thing would happen to the orthocenter of a right triangle. Maybe we'll find that out in just a minute. Ah, yes. The lines that contain the altitudes of a triangle are concurrent at the orthocenter. Okay, that's what we just said. The orthocenter can be inside, on, or outside. So if it's an acute, it's always inside. If the triangle is right, the orthocenter is on the triangle and it's on the vertex of the right angle. And that makes sense, right? Because in a right triangle, I can use this as an altitude, or I can use this as an altitude, because remember, they're both perpendicular there. And that's where they intersect, right there at the vertex of that right angle. And then, of course, with an obtuse triangle, the orthocenter will always be outside the triangle. Okay, I suspect we got some examples here. So here we go. R is the centroid. remember how I like to write this down? The centroid is the point of concurrency of the medians. And remember, the theorem tells me about the 2/3. So here we go. R is the centroid, SR. So SR here is 16. Find SV and RV. So what I know because of the theorem is that SR is 2/3 of the total length of that median, which is SV. Okay, well, I'm given that SR is 16. 16 is 2/3 of SV. So how do I get rid of that fraction there? I multiply both sides by 3/2. So SV is going to equal 3/2 times 16. So that would be 8. So SV is 24. If SV is 24, then RV has to be 8, right? The other piece would be 1/3. Simple enough. Okay, how about this one? Find the coordinates of the centroid C of DEF. Okay, the centroid. Okay, so here's a median. Here's a median. All right, and I need to know from here. So what have I got to do? I got to find the length of E. That's E. I got to find. So here's my strategy. Find the length of EJ, and then multiply that by 2/3, right? Find EJ, then multiply by 2/3. And this is nice because EJ is vertical, so I don't really have to use the distance formula. I can just count. So I got 1, 2, 3, 4, 5, 6. So EJ is 6. So 2/3 of EJ is going to be 4. So now I just got to count from the vertex 4 units. So 1, 2, 3, 4. So there's my centroid. And what are its coordinates? Well, it's over at 5, 1, 2, 3. C is 5, 3. It's nice when you're on a coordinate plane and you can just simply count like that. If it weren't on a grid like this, I suspect you would have to do a lot more work. Okay, here we go. Here's another good problem. Triangle ABC. We're going to draw us a sketch over here because you know that's the way we roll. Got to have those sketches. Triangle ABC has vertices at 1, 3, 2, 7, and 6, 3. So let me fill these in. C is 6, 3. B is 2, 7. And A is 1, 3. Okay, what are we trying to do? What are the coordinates of the orthocenter? Okay, what do I remember about the orthocenter? It's the point of concurrency of the altitudes. Right? What is an altitude? The altitude of a triangle is the perpendicular segment from a vertex to the opposite side. So let's do this. Let's drop one right here. Here's an altitude. There's an altitude, right? So B, I'm going to label that point D. And then I need one more, right? I need to draw in one more, and then I need to find their point of intersection. So how about that? Looks about right. So D, so I'll call that point E. So guys, here's my strategy. What I need to do is to find the equations for line BD and CE, set those equal, and then solve for x and y. You remember we did this in the very first lesson when we were finding the vertices of that big triangle using mid-segments. So let's think about how we're going to do this. First, we need the equation for BD. So let's write what we need. We need the equation for BD and BD and CE. Those are the two things we need. So let's start with BD. We need the slope, right? We need the slope and we need a point. How are we going to find the slope of BD? I hope you're sitting there thinking and BD is perpendicular to AC. So what if I find the slope of AC and then use the negative reciprocal? Yep, that's what I got to do. So let's find the slope of AC. And that's going to be, AC is horizontal. So the slope of AC is 0, which means the slope of BD is undefined, which means BD is vertical. I should have seen that without going to all this trouble. BD is vertical. Therefore, I know the equation for BD is just x equals whatever that x coordinate is. So therefore, x equals, and let's see, that's 2, right? That's over at x equals 2. So x equals 2 is the equation for BD. All right, that was simple enough. I just got to pay attention. If I had picked something other than BD, I would have had to do a lot more work. So this is good. Okay, now, how about I got to find the equation for CE? Find the equation for CE. First, I need the slope, and in order to find the slope of CE, I'm going to have to find the slope of AB, right? And then it's going to be the negative reciprocal. So the slope of AB is going to be 7 minus 3, which is 4, divided by 1. So 4. So that means the slope of CE is going to be negative 1/4, right? Because it's perpendicular. Okay, so there we go. We got the slope of CE. Here's CE. Just dotted it again. And now I need the equation. Okay, well the point that is on CE is this point C here. So I'm going to plug that into my point slope equation. Y minus 3 equals the slope, negative 1/4, x minus 6. So y equals negative 1/4 x. Negative 6 times negative 1/4, let's see, that'd be positive 6/4. So positive 3/2. And then I'm going to add this 3 here to both sides, so plus, and that would be 6/2. So y equals negative 1/4 x plus 9/2. So there's my equation for CE. And now, remember what I had up here, x equals 2, that's the equation for BD. So I'm now going to plug that in to find out what the y coordinate is. So y equals negative 1/4 times 2 plus 9, excuse me, 9/2. So that's negative 1/2 plus 9/2, which is 8/2, which is 4. So that gives me 2, 4. That is those are the coordinates for the orthocenter. So that's how you're going to do a problem like that. Okay, so guess what? We got one more of those here. One more of those. I'm going to want you to try to do this by yourself, looking back at the one I just did. I'll go ahead and give you the answer. because it's an answer that you're not going to like because it's a fraction and it's a crazy one, and you're going to say, it couldn't possibly be that. What is the length of the median? Well, let's draw the picture. We'll do that. We'll do that together. I'll draw the picture, and then I'll pause and let you do this. So DEF has coordinates 1, 2, 1, 6, and 4, 2. So here's our triangle. D is 1, 2. F is 4, 2. And E is 1, 6. Okay, what are the coordinates of the orthocenter? Okay, so the orthocenter, remember, that's the point of concurrency of the altitudes. Giving you some hints here. And then it says, what is the length of the median from vertex E to the opposite side? Okay, so you remember the median has to go from E to the midpoint of the other side. So I'll mark those two so you'll know that's the midpoint. So there's the median from E to the opposite side. And I'll go ahead and tell you what the answers are. Let's see, the orthocenter, that way you can know if you got it right or not. The orthocenter is at 1, 2. And part 2 of the question, the length of the median from E to DF is the square root of 73 over 2 units. Please take a crack at that. I'll be glad to work it for you in class if you need me to, or if you just need any part of it explained, be sure to let me know. That's it. Please keep working on those flashcards, guys. Study this vocabulary. It's essential. I'll see you next time.